Okay, for the last video in this series, we're going to talk a little bit about adjusting the parameters. And we talked about this early on in the series. If you open up the advanced and then click here, you can adjust the seed weight or the weight. And it has something here, min pairwise LCB score. So this one, you'd scroll it around, and this one, you'd enter any number you wanted into that. But you may be asking yourself, what do those things mean? I don't understand. Well, you see this little I button here? Let's click on that. And that gives you a description of the parameters. So the seed weight. The seed weight is used to generate local multiple alignments or passes during the first pass of anchoring the genome. And it says when aligning divergent genomes or more genomes simultaneously, lower seed weights may provide better sensitivity. So generally, with the Brucella that I work with, it doesn't do me any good to go below 12. And I'll show you some examples of that. It's kind of unsatisfactory. And if the things are less alike, you would increase the size. And I'll show you a figure of that to show you that you're going to see more blocks the more you increase it. If they are different genomes, you'll see more of those connecting lines popping up. The weight, you see, what is that LCB? That is the locally collinear blocks. And those are the areas that you see that the blocks in that. And so when you set that, that is setting the minimum number of matching nucleotides identified in those regions for that region to be considered true homology versus random similarity. So it's trying to find the best homologs between those genomes in a block, not an individual gene, but a block of genes. MOV uses something called a greedy breakpoint elimination to determine this. And if you want to know what that is, read the paper. I have played with this a lot. And at least for the stuff I work with, I have more success with the seed weight, adjusting that, than I do with the weight. But for experienced MOV users, go ahead, adjust these things, and have your way with them. For the rest of us who are not proficient at this, I find that the default works best. It's looking at what you've got, and it's trying to guess what will look best for you. So let's look at a few of these, and then I want to show you a figure that I created to give you some sense. And the first ones I'm going to show you are just those same 3 Brucella genomes. And remember, these guys are pretty highly conserved. So MOV was trying to create more blocks, but it couldn't. So we showed you the one that's set at the default. So we'll quickly look at that just to reawaken your memory of what that looked like. Oh, when that one loads, it just does my heart good because I think that's great. I think it's very attractive. And if I go back here, hit the back button, then I can go right into the workspace where I loaded those things. So I can click on this. So then I tried a seed weight of 10. And why am I messing with all these seed weights? I'm trying to get the best figure for a publication. Remember, a publication, you're telling a story. And you want the story to be illustrated for the reviewer and for the reader so that they understand what you're talking about. And the better those figures are, the more people are going to like them, the more the reviewers are going to have a better feeling about your paper if your figures are good as opposed to being lousy. So here I highlight this, and notice I can rerun it from here, but I double click on this job, and this was with the seed weight of 10. And then I click on the view, and yuck. That's why I don't like this for these 3 Brucella. I don't think that this is good for me. And so just to give you a sense, let's go up to 13. Remember, the default is 15. This is a 13. Let's look at this and click the view. Looks pretty much like the 15. And then let's go back, go here, And then let's go up to the top, the seed weight of 21. That's the highest, that's the max you could set it at. And let's click on the view. It looks the same. So what this is telling me is that for these three genomes, which are really, really similar, except for this one inversion, these guys look pretty much the same. But I've created a figure here for you to look at. And this is with two different Brucella genomes, one that's in a number of contigs, comparing those two things. So this is the 16M genome again, and this is a different Brucella genome, one that was isolated from a freshwater ray. So it's a pretty cool genome. So at seed weight 12, yuck, you don't want it. At seed weight 15, which is the default, you notice you have a lot of lines here. There's a lot of stuff going on. This genome is in a number of contigs, and there's been a lot of rearrangement. Does that mean that the genome is actually rearranged, or is it just the assembly because of how deep it could get? This wasn't assembled with PacBio, or it's not a hybrid assembly, so we're not sure of the order of these contigs, but there are a lot more blocks. And you see it's breaking up that Brucella too, the melitensis one, the reference genome, as it tries to adjust to that. If you go up to 18, even more. And as you go up to 21, even more. So I like to think of it as coarse versus fine. And depending on what you want to use it for, like you may really be interested in these rearrangements and what's happening in this genome. You might want it at this higher seed weight. But if you just want the pretty picture that's easy to understand, I would suggest going with the default. One more thing to note, when you have problems or you're interested in something in the service, there are different views here, and these videos will be accessible here, the information icon, and you can always go up into the help to get more information like the tutorials and things like that. So there are different ways to figure that out. So let us know if you have any questions, and I hope you enjoy using the Genome Alignment Service because that visualization is pretty cool. All right, see you later. Bye.